So welcome to the pre-recording of lecture 23 of MCS 572. So this lecture is a review of what we have covered so far. So we are in the middle of the course. In a way, the midterm serves to prepare for the computational science prelim. So there are some typical questions on it. And I will also, in the second part of this review, indicate some previous midterm exam questions. So the midterm will happen in the next lecture. So the next lecture will mark the milestone of having covered 24 hours of supercomputing. So there are two ways how you can approach this exam. As a paper and pencil exam, so this is in preparation for the computational science prelim, with the exception that in the course this is still an open book exam. Computers will not be necessary for experimentation, so you should be able to answer the questions with paper and pencil. For that you have time till the end of the day somehow. The alternative is to do the exam with computer use, but then you have more time. And it's still seen somehow as a way to kind of summarize the main important questions that we have covered on the material that we have covered thus far in this course. So in either way, you can consider this exam, if you're not interested in the midterm exam, as important homework. Okay, so in the first part, let's look at some past prelim exam questions. So the first question refers to the very early beginning of the course, where we considered speed up. So we have a run that was executed on a 12 processor machine. Of that run, it was observed that 5% of the operations were done by one single processor. So this is called the sequential time. The question is, can you compute the scaled speed up? So this is a very particular question. It seems at first that we are missing some data, so it doesn't really say how long the run on the 12 processor machine took. But even without this information, we will be able to compute the scaled speedup by the application of Gustafson's law. So let's look at the answer. So I copied the picture proof from the first lecture. So we have the 5% sequential time. So the 5% is factored in this parameter S. T is the total time. So with the picture proof, we have, in our case, 12 processors. So in the picture, we only have 4 shown, but the idea is the same. So we have the total time that's recomputed, the sequential time, and we divide this by t. So t is the parallel time. And now you see that if you have, after deriving the formula again, when we evaluate the formula for the 5% and the 12 processors, then we can compute the scaled speedup. So this is a question where you must know either the formula or be able to reconstruct and reinterpret the formula that follows from, or that is used in Gustafson's law. The second question is concerning a network topology, but also considers the application of an algorithm. So the hypercube network topology doesn't have sufficiently many or enough connections for to support a fan-in gathering of results. So a similar exercise was collected as homework. Here I work out one of the base cases. So a hypercube has a number of nodes equal to a sum power of 2. So the fan in here with 8 nodes starts from the uneven nodes that send to the even nodes, and then it continues where the nodes that are 4 apart from each other send to the lower ranked nodes, and finally you have the middle node that sends to the first node. So these are the communications that allow to gather one result to the root node. So in a hypercube, we consider the binary expansion of the identification numbers, and two nodes are connected when their binary expansion differs in exactly 1 bit. So if you look at the first stage, we indeed can verify that if we consider 1 goes to 0, 3 goes to 2, 5 goes to 4, and finally 7 goes to 6, that indeed we see that all the nodes are connected. So this first step is supported by the hypercube network. Look at the second layer. So in the second step, node 6 sends to 4 and 2 sends to 0. And again, we see that in the labels of the two nodes that need to be connected, there is only 1 bit different in the binary expansion of their identification number. And finally, 4 sends to 0, and also there we see that the identification number supports this. So the binary expansion, there's only 1 bit different. So in answering this question, so I talk a lot, but one should write what is the hypercube topology, what is the main characteristic that one can label the nodes so that their binary expansion differs only in 1 bit. And this shows the solution of this problem for the base case. So here I worked out the largest base case, but it would essentially already be sufficient if you would verify this for 2 nodes. Then in the induction proof, we go from 2 to the power k to 2 to the power k plus 1. And what essentially happens is that in the first k steps, you could see the hypercube with 2 to the power k plus 1 nodes as 2 hypercubes of a lower dimension, each with 2 to the power k nodes. And then you see that in the first k steps, you can apply the induction hypothesis. In the first k steps, you see that we have the first hypercube, everything gets there gathered to node 0. And because of the induction hypothesis, the hypercube with 2 to the power k nodes does have sufficiently many connections. And also then in the second half, everything is gathered at node 2 to the power k. And then in the last step, you go from 2 to the power k to 0. Similar like in the previous slide, you go from node 4 to node 0. And then there's only 1 bit different. Okay, so this was a theoretical exercise. In the next question, again, we are on the computational science prelim, And you should imagine that these questions are closed book. So you have to know the concept of work stealing. So, what is work stealing? What's the purpose of it? And describe um, an example of an application, an environment that uses work stealing. So, this is a historical question. In the case when I was um, only aware of, been made aware for work stealing when with the Intel threading building blocks. So that's why I'm listing it here. But of course, we can also see work stealing as a job scheduling strategy where the processors are actively looking, where idle processors are actively looking for jobs and they are stealing the jobs from other processors. So here is the definition between job scheduling done by one scheduler, one central algorithm that's executed by one node. Think about manager-worker paradigm in distributed memory computing. In work stealing, you have that the idle workers are looking for jobs from other processors. So one application, we had an exercise by computing permanence this semester. Another application is the computation of a game tree where you would distribute it uh, according to the first 2 or 3 levels. You would distribute the threads, each have their investigation of the 3 levels in the game tree, the first 3 levels, but then they need to be responsible for all nodes that are below their levels. Now, in a game, in certain moves, it can be over really quickly. In other parts of the game, it could actually take a long time, and an idle worker that was assigned one part of the game tree could make itself very useful by looking into uh, helping the other nodes. Okay, so last question, or I would say last question of prelim type. Define data parallelism. What is data parallelism? What type of parallel computers do data parallel tasks? And also relate your explanation here to the classification of Flynn and describe a programming model that exploits data parallelism. So what is implicit in this question is graphics processing unit. So this is essentially one of the terms that you would need to know, or that would need to come immediately into mind after all what we have gone through in the first part of the course. In your answer, what is important is that an application is data parallel if arithmetical, if the operations on the data can be done independently. So one classical example, one very easy example, when we considered an easier introduction to data parallelism, to GPU acceleration, was the addition of 2 vectors. So this can be performed, every sum operation on the elements can be done independently from all the other ones. So this corresponds to instruction level parallelism. So in very early on in the course, we had the classification of Flynn, and this 1966 classification still applies here. So we are executing the same instruction. So in the example of vector addition, the same instruction, the add of 2 floating point numbers on multiple different data elements. So there is the compute unified device architecture. defines a programming model that is derived from graphics processing, and the unified device is what we have discussed. It's unified in the sense that graphics processors may run in uh, graphics processing mode or in general purpose computing mode. So in this model, blocks of threads are launched on data. So it's a scalable model. If you have two streaming processors, if you have four, if you have eight, you can adjust the launching the distribution of the blocks of threads um, very nicely. And the key uh, device architecture here is the graphics processing unit. So there is not a canonical unique example, unique solution for these type of questions, but the solutions that are given here kind of give the critical, the important, the most important information that should be contained in a correct solution to these questions. Okay, then let's look at some previous midterm exams. So here in this case, I actually do not have the answers mapped out, written out in great detail. So let me explain what the problem here is. So we consider the composite trapezoidal rule applied to quadrature. So we have an integral of some function over an interval a b, and we are considering this distributed memory computing. So what do we have? We have n subintervals and m number of floating point operations needed to evaluate the function. So actually to apply the composite trapezoidal rule requires n plus 1 function evaluations. This n plus 1 needs to be multiplied by m, and actually we also have the summation and then the multiplication with the length of the interval. So on the midterm exam there is a paper and pencil part, and actually then there's a computer part. So the idea is also a little bit if you have thought about the paper and pencil part, but you somehow feel still quite uneasy if you haven't experienced this on actual code and ran some examples, then the work that you spent on analyzing the problem will not go to waste if you do the homework using a computer. So it takes a while to let this problem sink in a little bit, and the time of, say, on an actual 50-minute exam might indeed not be enough here. Although one could see that this is easily a pleasingly parallel computation, the minimal communication cost is that every processor sends the results back to the manager. So one could even have the nodes if the program starts. So here now we are in a single program, multiple data environment, where you could have every node compute, given the A, the B, and the N, you could have every node compute where every subinterval begins and ends. So the key word here too is data parallelism. So the interval A, B is splitted into n subintervals. And actually in the finest way you could do this with n processors, so n equals p. So there is a limit already on the scalability. So the number of subintervals, one would typically divide the subintervals over the number of processors. So the computation time is this m times n plus 1. If you want to be more precise, you also have the n additions and 1 multiplication. So there is the communication costs. So in the most frugal case, in the optimal case, the nodes would not do any communication in the beginning, but they would still need to fan in the results to the manager node. So this would require a logarithmic number of steps, logarithmic in the number of processors. Now, the problem there is that there is so little communication, but it happens all at the end. A fan-in would actually be quite good, and because otherwise, if you think about a million of processors, if you scale up to large number of processors, this fan-in would definitely be required. So in describing the high-level parallel distributed memory version, you could start out with the computation or the distribution of the parameters A, B, and N, or you could have that computed, but in any case, the communication of the result, so where every processor has computed its approximation over the subinterval, where that happens. So this is a pleasingly parallel computation. So if you work with P processors, you would expect that the speedup is close to optimal. Efficiency is speedup divided by the number of processors. So in a way, you will have to describe the efficiency. If we think about the scalability, obviously, how far can you go with your number of processors? It does not take, in this formulation here, it does not make sense to have more processors than you have subintervals. That's an obvious limit here. But also already it may very well be that n has to be much larger than p, so that you will do much better off when several processors take multiple subintervals. Okay, so that's the first question. If you do this in the computer version, you can define with MPI for pi, MPI the Julia's, or even the C version. You could do it there and experiment to examine the scalability. In this next example, this next question, we consider the computation of the enclosing intervals of all roots of some continuous function. The way you could see this is via a tree structure, but actually this is not the right way how I set up this problem. So what you want is you subdivide the interval and you have to make all these function evaluations. If your granularity, so if you work over the interval 0, 1, and your delta is 10 to the power minus 6, so that means that you are dividing the entire interval 0, 1 into 1 million pieces. And there are all these function evaluations that you need to do to locate the roots. So you have 1 million intervals, and at the left and the right hand side, you need to check whether there is a root inside the interval using this test from the bisection method. So in a shared memory parallel computation, you could think of all the tasks that are generated. You could also think about the Fibonacci numbers. So the generation of every subinterval can be done with a recursive algorithm, where the base case is when the b minus a, the length of the interval, is less than the parameter delta. So this in the course we have seen the tasks with the parallel generation, the recursive generation of tasks, and actually here this would apply. How does work stealing apply for this? Well, it would apply in a scheduler, the one that is used in the threading building blocks and other runtime environments. But you could also see this as a job scheduling strategy where you would partition, where you would first use a course partition, or you would just have um, the if you run the bisection method, you could again see this. We had the other work stealing question with the game tree. Something similar may happen here if actually the sign changes are. So you could work with um, also here a case where you would not be interested in all the roots, but perhaps all those for which the bisection method applies, and start subdividing in that way. So, I mean, what I want to say is that you start with your, if you have P threads, you would have P queues of tests that need to be worked out. So the P would be matching the subdivision, the very coarse subdivision of the interval, but then some of the subdivisions would actually drop out. Okay, next question is also on multithreading. So we consider the orthogonalization of a sequence of vectors. So this is one way to compute a QR algorithm. It's actually also very beneficial here to think about the geometric interpretation of the Gram-Schmidt method. So what the Gram-Schmidt method does, it goes through the columns, it orthogonalizes the columns by projecting the next column onto the column space. So subtracting from the current column these coefficients, the projection coefficients. So here you see there is a double loop, and the second part of the loop can actually be run partially in parallel. So allow me to explain this. So this is a two-sided question. So you would think about the formulation of the algorithm that it is a quadratic, so it's quadratic in n, but the length of the vectors is m. And I don't know if the question actually is sufficiently. Yes, so the m is the length of each vector. So you could have you could have many rows where the m is a lot larger than the n. So in that sense, you have relatively few vectors, and you shouldn't really consider the parallelism at the outer layer. But you should consider the computation of the inner products. Now, the computation of an inner product in parallel. So for two vectors, you compute all the component-wise products. It's obvious that if you have a vector of length n, so this is also computation that can happen in n independently executed instructions. But then you have the fan-in algorithm again. It's similar. So in this context we actually call it the prefix sum, and that in this fan-in you can actually then in the logarithmic in the size of the vector, in two log steps in the size of the vector, you can then compute the inner product. So that would describe the finest granularity of the algorithm, where each time when you compute an inner product, you launch actually always up to m threads or m tasks. So every instruction that you see here would actually be executed. So there would be one parallel region for the entire algorithm if we think about the OpenMP formulation. So in the computer experimentation, this could be done with an OpenMP program where all the instructions that you see here are actually operations on vectors, inner products. The second question was also, when I look back at it for the first time again, a little bit confusing. So here now we consider in step 2 a different kind of parallelism. And here it's very useful to go to the geometric interpretation of this Gram-Schmidt process. So what happened, it looks like a very sequential process. So each time you consider, so K runs through the columns of your matrix A. So progressively you consider more and more vectors. But there is some parallelism there. If you have already orthogonalized, or if you consider, say, the first column in your matrix, you can subtract the orthogonal projection of all the other vectors onto the first vector, and that can be running in parallel. So there is this triangular structure in the K that runs through the columns. So there is a lot of parallelism in the beginning, and the parallelism actually declines. So the length of the critical path is n, is a number of columns that you have. The length of the critical path is not at all constrained by m, where m, so here now you consider a larger granularity when you think about the task graph. Okay, so 40 minutes budgeted for this lecture. I probably won't need that much. The last question is for the compute to global memory access ratio of an iterative method to solve a linear system. So Jacobi's method is a very simple method. So there are actually 3 steps in it. So what are the questions here? Is this suitable for data parallelism? So how can you write a data parallel version of this code? Well, there are 3 steps. Actually, it would be better to read this from right to left. So the third step is essentially vector addition. And vector addition is something that we have encountered also when we solved the prelim question. So that is one kernel that does the vector addition. So this can be done in data parallelism. So the second kernel is also quite straightforward. We compute the components of the update by dividing by the diagonal element. And actually what we first compute is a residual computation. We subtract from the right hand side the matrix vector product. So one needs to define 3 kernels here. The first kernel is actually the most one that is involved, and this can still be this actually should probably be separated in 2 separate kernels. We have the matrix vector multiplication, and then we have this difference, which is actually the same kernel as the vector addition, only with the sign flipped. Instead of adding, you subtract. So there are 2 kernels in A actually. So the main interesting kernel to define is the kernel to do a matrix vector product. If you compute the compute to global memory access ratio, it's actually not that good because you know, and if the matrix is an n by n matrix, you have already n by n data elements there. And also you have n square plus n because also you have the vector you're multiplying with. And if you like, you also have the vector where you have to write the result to. So you have n square plus 2 in the memory accesses. And as far as the computations go, also that is essentially quadratic. So we are executing n inner products, and every inner product is linear in the so the compute to global memory access for one row in this inner product, you have n multiplications and n additions. So you have n square for the number of computations and n square plus 2n for the memory accesses. So if you have to do one inner product, one iteration, it can be quite expensive. However, the entire matrix would already reside into the global memory. And actually, one can arrange it probably better also that one can exploit the memory hierarchies. But for this course, for this topic in the course at this point where we are, it would be sufficient in the computer version of this exam to, for example, use Julia. And in Julia, we can write kernels at a very high level. Okay, so this review went for me quite well. I hope that I was not so confusing. So the purpose of this review is to illustrate some of the major concepts we have covered thus far in the course. So we have distributed memory computing, which is typically implemented with message passing. We have shared memory, parallel computing. We have threading and tasking. So if there are 4 questions on the exam, the middle questions would be one on more focus on multithreading, the other more on tasking, and concepts like task graph are important. The last question will be on GPU acceleration question. Very similar to what we have here. There is the definition of the kernels. Verify that you do have data independence, that data parallelism is possible. And then be careful about the memory movements. So again, is a computation memory bound or compute bound? That is the big question each time. So I hope that this review somewhat prepares for the upcoming midterm and also gives somehow a review of some of the most important problems and concepts we considered in this course thus far.